Hello everyone, myself Kirish with ABAQUS tutorials. So today I'm here with the durability, that is fatigue analysis on the basketball ring, as you could see here. Okay, in this session we'll go through the stress strain curves and basics of the fatigue analysis, how we need to deal with this, and different types of criteria like Goodman criteria, Gerber criteria, and the Soderberg, and even we're gonna deal with the high fatigue cycles and the low fatigue cycles. Okay, these things around we'll go through. Before that, we'll see the basics. So it basically originated from a Latin word that is fatigue, which is known as to tire. Okay, so everyone will get tired, no? Same thing after a certain amount of time, whatever the material or whatever the component we're gonna consider, it will go to tire. Okay, the terminology is a damage and failure of material under the repeated cycles. Okay, that is cyclic loadings. So this is all about the basics. You can just go with this. So it is just a progressive, localized, permanent structural change that occurs in the material subjected to the fluctuating stresses and the strains. Okay, that will directly leads to the crack propagations after a sufficient number of fluctuations. Okay, so there might be high fatigue cycles and low fatigue cycles that we'll see now. Okay, so these cyclic stresses are normally well below the yield strength of the material. Okay, so we're gonna consider only the fatigue analysis that will lie under the yield strength. Okay, if you're considering high fatigue cycle, so that will be under the same thing. So as you could see, this is the cyclic loading. Okay, this is fully reversed. Okay, it is 1 to -1 you can consider. There might be some cases zero biased, that is zero based as well. So it will, like, initially it will load up to a certain loading condition. Let's say from 0 to 1. Let's say I'm applying the 500 Newton, 0 to 500 Newton, and again it will come to rest. In the sense, the loading will be removed. It will not be again minus 500 Newton downwards, as you could see in the curve. Okay, that is 0 to here, like this. So that is known as zero based. Okay, so there are different types of fatigue failures. One is the mechanical fatigue, that is due to fluctuations in the external applied loads, that is stresses and strains. Due to this stresses and strains, due to this the fluctuations will be created, that is known as the fatigue, that is mechanical fatigue. The creep fatigue, in the sense, due to the high temperature with the repetitive loading conditions. Okay, same thing, we have thermomechanical fatigue, the fluctuation in the temperature as well as the stress and strains, everything will be considered there. The corrosion fatigue, what exactly it is the cyclic loads in a chemical, aggressive, and embrittling environment. And then we have the fatigue. Okay, this is a cyclic loads combined with the frictional sliding as well. Okay, so these are the few things, and the same thing will be explained here. Low fatigue cycle, which and all will be considered, and the high fatigue cycle, and this is the endurance limit. This we'll see in detail in the next slides. Okay, yep. So here there are some description about the stress strain curves. You need to remember, if you're going to deal with the fatigue analysis, we need to know about the stress versus number of cycle curves. So that is mandatory. And with respect to that, some of the rules will come into account, that is criterias, that is Goodman, Gerber, and Soderberg, and Brown Millers, and there are different criterias are there. So here the first thing is we have the number of cycles. Okay, it is e raised to 7, that is, you could see 10 into 10 raised to 6, or e raised to 6, e raised to 7. We can call it as 10 e raised to 6 or 1 e raised to 7. So this is the maximum cycles we're gonna consider for the fatigue analysis. Okay, if it is more than that, it is high fatigue cycle. If it is less than that, it is low fatigue cycle failure. Okay, so as I could see, the low cycle, in the sense there will be high stresses in the model, okay, which will be due to the plastic deformation, not in the elastic region. So these are the low fatigue cycle. Okay, there will be high stress. Due to that, the elastic deformation will happen, and with that, the fatigue failure will occur. So this is the some description about it. We can just go through this one. And coming to the high fatigue cycle, so there will be a low stress fatigue, we can say this one. So here what exactly happens is, the whatever the deformation will be there, the fluctuations will be there, it will be in under the elastic range. Okay, as you could see, material deforms elastically. The same thing, there are some explanations, you can just go through this. Yep. So there are some things, that is crack initiation and crack propagation and the ultimate failure and all, and the crack growth. So that and all the basics are there, you can just go through it. Coming to the ascent curve, as I said, so the behavior of the material in the high cycle fatigue is characterized by the relations between the alternating stress and the corresponding number of cycles to the failure. So this is represented here in the uh, graph. So as you could see, this is 10 raised to 6, in the sense e raised to 7. It will be the fatigue strength of each and every material. So this endurance limit, you could see, it is 10 raised to 7 is the cycle. So we can consider, if your component has the fatigue cycle more than 10 raised to 7, your model will be safe enough. Okay, it has the higher lifespan, so unlimited lifespan we can consider. Okay, yep. So these are the approximations points you could see. This is the practical testing we can consider. Depending upon that, this curve will be drawn with respect to approximation. Okay, so from this only we're gonna get the stress versus number of cycle curve, and that will input with the fatigue analysis to get the results accordingly. Remember that. Yep. So coming to the fatigue strength, as I explained, this is the stress at which the stress failure occurs at the given number of cycles. Okay, the failure will occur at the number of cycles, and is known as fatigue strength. So that much cycle it will withstand, in the sense after that it will fail. Let's say 50,000 cycles, so that is the fatigue strength of the model, that is 50,000 cycles. After that it will fail. So endurance limit is the limit where you can consider it as the unlimited lifespan, that you could see. Endurance limit is the highest alternating stress that does not result in the fatigue failure. That you need to keep in mind. Okay, in short, you can go through this all the details, or you can read it to understand more. Okay, you could see we have the fully reversed stresses as well. Okay, coming to the criteria, so first one is the Goodman criteria, which we consider for the brittle materials. As you could see the curve here, this is the Goodman criteria curve. So if you're dealing with the brittle materials, better deal with the Goodman criteria to deal with this. We have the Gerber, that is experimentally known as that is ductile, that is only meant for the ductile materials. Remember that, Gerber. The Gerber curve, you could see here, this is the curve which is used to deal with the ductile materials and the Soderberg. So it is the curve which we will refer when yields conservative results in the tension. Okay, so you could see these are all the curves and how they're gonna implement on the results. This is the model on which I'm going to conduct the durability analysis, that is fatigue analysis, so that we can cross check the lifespan of this particular model with respect to the loading. Okay, well, so first thing is I need to conduct the static stress analysis From that particular loading, I need to carry out the durability analysis by using the solver called FE safe. Okay, let me just deal with the stress analysis first at the moment. So the model is already imported, so it is a step file, so which has been downloaded from the GrabCAD. Okay, the first thing is I need to define the section. So let me just showcase the same thing. So I need to assign the section, so I'll create the section. So I'll select entire model, whole model. This is the first step you need to remember. Section assignment is very important. So once you do it, from here you need to define the material. So before that I need to create the section that is solid and the homogeneous type I'm gonna choose for this. If I click continue, you need to assign the material. In ABAQUS you need to manually define it. I'll take the steel into account. So from the general I'll define the density. So 7.850 e raised to 9. I'm considering megapascal, so you need to define the unit SI unit depending upon the megapascal range. So you can check the SI unit conversions on the initial page. Okay, so elastic, here I'll consider this as my value. Okay, 2.03 into e raised to 5. Poisson's ratio is 0.33. I'll take into account. Okay, so this is the initial section assignment. Once you are done with this, you can proceed further now. Material assignment is done, and then now assembly. From here you need to define the instance. So I'll select the part that is a dependent mesh on the part. I'll click on apply and OK to continue further. Okay, so once you're done with this, you can proceed further. The next step is to deal with the step assignment, that is to deal with the type of analysis you're going to deal with. In the static general, I'm having the different types of meshing, analysis, that is dynamic and the implicit explicit analysis. So if you switch the to the linear pore distribution, there you can conduct the buckling, frequency, as well as different types of analysis here. But at the moment I'm going to consider a general static analysis. Okay, continue with the same thing. So it will ask you for the time period and all. I'll keep it as default one for the static analysis. Increment and all, if you want to change you can do it, but as it is static analysis, I'm not going to change anything. I'll keep it as default. So once I assign the step, I'll go with the interaction. So I need to assign the interaction. So fine. So here I need to define the RP point. So for that I need to create the partition on this model. So exactly on the center of this I need the partition. So I'll go to the part. So from here I'll use the partition face sketch. Okay, I'll select it. I'll just select this face as a reference. On this I'm going to apply the force, right? So I'll click on sketch origin, auto calculate. It will automatically calculate the origin. So it will ask you for the vertical and on the right. So you just select the vertical reference edge so that it can align it and you can create the sketch. So I'll draw a line from the center like this. So it will automatically try to snap the mid. So here it's the midpoint. You can press escape and click on done. So automatically on that position the partition will be created. So why this partition is because I need the center point to define the concentrated force. Okay, so here you cannot directly select the face and define the force. For that you need to define the contact sets, defining the reference point and all, and then you need to define the force. I'll showcase how to do it now. The partition is done. I'll go to interaction. So here I'll define the reference point. So that reference point should be on this midpoint. Okay, RP1 is created, that is reference point 1. So once you are done with that, I need to create the constraints, that is create constraints tool. You can use it. So here what you want to do, so I'm gonna deal with the rigid body constraint, not the tie. So just click on continue. Here you need to define the reference point. I'll click on this icon, that is edit, and just select the reference point 1 to define it. So it shows the reference point 1 is picked. And now here, what exactly you want to do? I'm gonna pin it, not the tie. Okay, it is kind of welded. Okay, remember that. So bonded kind of stuff. So you just click on this and just select this icon to select the selections. So you can hold the control or shift and select these two faces. So these two faces will be bonded with this RP point now. Click on done. As you could see, this constraint, they are with respect to the reference point 1. Here the points has been created. So if you apply the force on this RP point, it will be distributed on these all the nodes. Okay, fine. So that is done. So once you are done with the interactions, you can go with the loading conditions. On the loading condition, I'll define the fixture, that is this face, into account. So once you do that, you can use this option, that is encaster all the degrees of freedom are 0, so it is completely fixed. Okay, and then the force, the concentrated force. So this force you can't apply on the faces as you do in other softwares. Here you can only apply on the reference points or the nodes, remember that. So for that I had created this reference point. For this reference point I had constrained the nodes on these faces. Okay, so that it will be equally distributed on this face. The force whatever you're applying on this particular RP point, it will be distributed on this. Okay, yep. So continue, just select this RP point, click on done. So define the force CF1 2 3 along XYZ direction. So I need it along Z direction, so I'll take it as minus 100 Newton. So you could see the direction is downwards. For your reference, I'll just make it aligned like this so that you can understand. So it is done. After the loading condition, I need to mesh it. I'll go with the mesh. So you need to, if you click on the assign mesh control, it won't take it because you need to switch to the part mode, and then you can just select the mesh controls, and here you can select the type of mesh controls you're gonna define. I'll take the tetrahedral mesh into account. Only technique is free, remember that. So once you're done with that, you can assign the seeding part. So here approximate global size, I'll take it as 4. The curvature control, you can just keep it as point, let it be. I don't want to, okay, I'll make it 0.075, and here also 0.075. Apply. You could see at these regions it is a kind of refined one. Okay, click on OK. So here if you want to change the background, you can even do it. Let me do that. You can go to view, and from there graphics options, here the top I'll keep it white, and the gradients also I'll keep it white. Okay, click on apply. That's done. Okay, the meshing is also done. So oh no, I need to mesh it, right? You need to select this option, that is mesh part. Just click on S. Okay, so there is something wrong with my model, so I need to deal with this region. So as I could see, this edge has some issues. So again for that I'll switch to the part. So I'll use the geometry edit. From there I'll just deal with the faces. So I'll use the reface small. I'll select whole model. I'll click on done. I need to update the model. I'll simply click on repair. So after that you need to update the validity of the model. Just say yes to update the validity of the model. So as you could see, it got automatically refined the 78 solid faces, 212 edges, and 130 vertices. Just click on done. Okay, now switch to the mesh and try to mesh the same thing again. Let's see. Yeah, so it will refine the mesh, and it will rectify everything, and it will automatically solve each and every errors with respect to the geometry settings which we have done, that is face repair, so that you can easily mesh the model without any errors. Okay, this mesh is fine for now, so I'll go ahead with the job creation. So here you need to create a job, double click on it. Okay, job one, I don't want the name as job one, I'll take it as fatigue. Okay, or else durability is also fine. I'll click on continue. So it will ask you for the initial inputs, that is job type full analysis. So at the background I want to run the study, and the remaining steps, the memories and all, you can define it. 90% of the memories will be utilized for this. Okay, the job is created, durability, right click on it and submit, so that software will run the analysis. So as you could see, it shows a running, and then after a few minutes the solver will solve for the stress and the displacement results by dealing with the partial differential equation, that is F, which is equal to stiffness matrix into displacement K into U. Okay, in reference to the Poisson's ratio, it will try to solve the entire model at each and every nodes. Okay, and then it will give you the results in the form of displacement and stress. Yeah, the analysis is completed now. You can directly switch to the visualize to check the results. Okay, now you need to load the ODB file. If you just click on it, you get the notification that there is no output database, that is ODB. So to load it, you need to go to file open. Okay, just click on open and just select the ODB, that is durability.odb, which we have recently ran the analysis. Now that one, this is. Click on OK. Software will load this file. So could see the mesh now. So this is the mesh one. So you can switch to the plots. You could be able to see this. Okay, so the stress results, you could say it is 108 megapascal. So the ultimate strength is 375 megapascal, I believe. We can cross check with respect to the data which we had selected. Okay, so I need to make the settings inside the model. So auto compute, this is fine here. I'll take the no edges, apply. Okay, and okay, to turn off the let's say you have the both the options, that is one is deformed and undeformed shape. You can turn off by using these sections here. I'll simply use either one of these two at the moment. Okay, so as you could see, this is how the deformed. Okay, so I'll switch to the displacement results. Displacement is hardly 1 mm. Okay, 1.05 mm we can consider, only 1 mm. No, so this is the results, okay, which we are taking into account. So now what we can do is we can directly switch to the FE safe analysis now. You can use the FE safe which you have installed it. If it is not installed, you need to purchase the license and install it separately. It is a separate independent solver. So I'll create a new project, so that is durability. Okay, so you can even specify the location. Let's simply click on create. So this will be created now. Uh, from here I'll choose the material, that is I'm only looking for the steel. I'll use the uh, that is Muntin steel. I'm using it into account at the moment. Okay, so you can simply select this. Now I need to load the project. You can use the FEA and FEA solutions, open finite element model. So the model which I'm going to deal with this is this one, that is durability. So it will ask you for this free scan. So I'll just say yes to scan the entire model. Once you give it for scanning, what exactly happens is the FEC will load the entire analysis and what and all the analysis you have done. Okay, so I'll take only the stress results into account. Okay, only the last increment I'm going to consider. If you're dealing with the nonlinear analysis, it will have the multiple increments. Okay, I'm concerned only with the stress. I don't want the strain results to be included here. The forces I need into account. I'll simply click OK. Okay, so once you're done with this, you need to define the unit system here. So I had considered the megapascal into this static analysis in ABAQUS. So same thing I need to consider it here as well. So it will ask you for the unit system definition. There you need to define the same thing. So as you could see, it load all the elements. So once it is done, it will give the input for the unit system so that you can define the same thing. Okay, as you could see, I had considered the stress units for as MPa. I'll select the same thing, remaining everything is same, force in newtons and the distance in millimeters. Click OK. So it will ask you for the rating the group. So I'll simply click on S. Yeah, now this is the analysis group. It will take all the elements into account. If you want, you can remove the elements which you don't want. Let's say I don't want this bond element distorted. You can simply select this one and you can move this side, and only these will be uh, taken into account to solve the durability analysis. Okay, I'll click on OK. Yep, so as you could see, the surfaces and all the stuff will be taken into account. Now the SAE 950C Pantene material is taken into account. To check the properties, as you could see, the algorithm by default is Brown-Miller. I'll showcase how to deal with this. The material class is steel ductile, it is taken into account. Okay, and the Young's modulus is the same thing which I had taken into account, that is 23,000. Okay, Poisson's ratio is 0.33 as I taken into static analysis, right? And the ultimate strength is 400 megapascal. I had told you it is 350, but ABAQUS will give you the results only. It won't check with the ultimate strength and all. Okay, here you can able to cross check that one. So the same thing, the SN curves, if you want to check, you could see these are the stress values 363. The number of cycles will be 10,000 for this value. For 188 it is 10 raised to 7, right? 1 into e raised to 7, that is 10 raised to 8 somewhat. 10 raised to 6, no? Yeah, it is 10 raised to 6. 1 into e raised to 7 in the sense. If I add 0 here, it is 10 raised to 6. Okay, 188. So our results is around 108 megapascal. So it will be more than this, right? 10 raised to 7. We'll see this 10 raised to 6, right? We'll see the same thing now. Yeah, so I'll double click on this. You need to select this. Okay, that is 950C Manton. You need to select this. As you could see, you need to click on this and then you need to double click on the material so that whatever the material you have selected here, it will be replaced here. You could see it will be replaced with the SAE 950C Manton. I'll say yes. The material will be applied for all the elements. Algorithm by default it is Brown-Miller, but I want to change it. So I'll use the different algorithm. Let's say I'll use the von Mises Goodman at the moment. Let's see how it gonna change. Okay. So this is the first analysis we are conducting. So once you are done with these all the options, algorithms and all, here it is SN scale, and here residual stress, and this is a surface finish. So if you have like surface finish clear, you will have the KT value, it is 1. If you have the different types of surface finish, according to that the surface finish constant value will be changed, like 0.7, 0.6 depending upon the surface finish. Okay, remember that. Well, so once this is done, you need to define the output file to evaluate your results. So for my convenience, to make it easy, I'll just select this one here. The folder I'll create on the desktop, durability analysis FE safe. I'll consider this folder. I'll open it. I'll read the results. I'll take it 1. Okay. Yeah, the output folder got synced. The source we have taken as ODB file, that is durability, which we have conducted on ABAQUS recently, right? So I'll switch to the loading settings here. So in the loading settings, I need to change it. You can completely remove it and you can create new. So that also I'll showcase. You can delete this data set, or else you can simply add the new one, but I'll make the changes into this only here. I'll make it 0 to 1. So in all the softwares you have seen, it is like a fully reversed or zero biased, like that, right? Zero based and all. So it is zero based in the sense it is like this 0 1. Fully reversed in the sense 1 to -1, the same loading. So here consider zero based, that is 0 to 1 only. So it won't completely like for example, I had applied the 100 Newton load, right? What exactly happens is it will take the 100 Newton load once and it will come to 0. It won't go reverse like -100 Newton load. So that is fully reversed. So like this, only 100 and relaxed, 100 Newton relaxed, 100 Newton relaxed, like this. Okay. 0, 1 I had defined. I'll click on OK. So I had defined my stress database. So once you're done with this, I need to analyze this particular whatever the inputs I had given. You can go back to analysis settings here and simply click on analyze. So what software does this with respect to the Goodman study? It will give the solution for you. So at the background it is running. As you could see, results started. Here you'll get the notification. You can even maximize this, or else once you get the results, you'll get the window to check the results. Yep. You could see worst life repeats. There is no damage, as I had said. Our one message results we can check now. As you could see, it is there is no worst life repeated here. Let me just showcase the results with respect to stress. It is 108 megapascal, so it should be more than that. So now whatever the results I got it there, I need to visualize it now. So in FESAFE you can't do it. It will just solve the model and it will give the file. So you should load that one here. Remember, it is 108 here, 108 megapascal for the stress analysis. So what I'll do is I'll open that model now. So that should be on the desktop. So this is the file 1. I'll load this file now. So I'll switch to this. You could see everywhere it is 10 raised to 7. Sorry, 10 raised to 6 it is. Okay. And there is no failure occurring on this model with respect to that. So it is a high fatigue cycle. So it is more than 10 raised to 7. So the life validity is more. It is unlimited, we can consider now. So what I'll do is I'll switch to the FESAFE now. I'll try to change the loading options. Instead of this, I'll edit this one. I'll make it 2. So what happens is whatever the loading we have given, it is multiplied by 2, around 200. Okay, the load we have given is 100 Newton. Now it is 200 Newton. Okay, 200 Newton, it will go to 200 Newton, again it will rest, again 200 Newton and rest. It is zero based. Well, so I'll define the output file. I'll change it to 2 because I do want the first results should be saved. The second is also I need it for the reference purpose. So same Goodman SN curve I'm taking into account. I'll run the analysis. So these curves, whatever we are considering for the solving, Goodman, Gerber, and the other Soderbergh, and even the Brownie Millers. So these also factors a lot while dealing with the analysis. Remember that. I'll showcase that as well here. So analysis is running in the background. Let us see. So still it doesn't have any of the issues. Okay, no issues. I don't need to review it. So let's again change the loading cycles here. I'll consider the 300 Newton now instead of 200. Click OK. Output file, I'll make it 3. The 3 in the sense 300 Newton. Remember that. Okay. I'll run the analysis again. Yep. So for 300 Newton, we have the worst life condition, that is it can withstand only 37,837 cycles only. Okay, so these elements are failing at that region. So now this is what we got it with respect to Goodman cycle, right? So I'll just simply load it and I'll showcase. You can go to the open files, and this one we need to load it. Just load it. Okay, you can switch here and you could see it is 10 raised to 4. It is not 10 raised to 4, it is 1 into e raised to 4, 10 raised to 3 in the sense. Okay, so results might not be more clearer at this region due to only few elements will be failed. Okay, so for that this is like this. If you want, you can change the options. For the spectrum, you can use the reverse rainbow, apply it so that you can rectify the same thing. So again, to cross check exactly where it is failed, what you can do is you can go to this option, that is failed. Let me just check. Okay, I'll go to this. Yeah, as I could see, only these regions, this one, that is somewhere failing at this. You can rotate the model, you'll get the symbols. Okay, these are the ISO surfaces, so only these regions are failing. Okay, yep. What I'll do is I'll go to the model. So instead of Goodman, I'll change the algorithm to someone like I'll take the Gerber. Okay, Gerber for ductile, right? Let us see that as well. I'll analyze it. No, wait, I need to change it right here. I'll make it 4. So this is for 300 Newton. We're running it for Gerber. Yep, for Gerber, it has more cycles. As you could say, it is 1, 2, 3, 4, 5, 6. 10 is to 6. It is 10 is to 5 actually. Okay, 18 lakh cycles are there. Let me just check. 18 lakh 12,808 cycles. So with respect to Gerber, it is more cycles. Okay, Uh, Wait. So even you can try with the default one instead of Gerber. By default for this, it is program default, that is Brown Millers. With that also we'll try. So what will be the results? We'll see. Okay, it is 31 lakhs this time. This is also fine. So with respect to ductile, this is 31 lakh. Okay. Now instead of considering this one, I'll go with the Honeywell project example. So it is ductile. It is the algorithm is normal stress versus SN curve. So with respect to the SN curve, it is taken into account. Okay, that is, you could see the SN curve here, 1000 for 905, 1000 Newton. No, it is stress value 905 megapascal will be 1000. So like this, it will vary. Okay, let's see. We'll take this model into account. That is Honeywell example. I'll change the material here. Okay, now by default, I'll take the ascent curve into account. Material default. I'll change it to 6. Okay, this is for Honeywell material example with respect to ascent curve values it has taken. Okay, same Poisson's ratio is 0.33 only. Don't need to worry about it. And the same thing. Yep. Let's see with respect to this, what will be the result? Okay, with respect to this, it shows 80.92. Okay, so it is the worst case, so it will definitely fail. Okay, we'll take this one and we'll analyze it in the software. Okay, I'll just open the model, the last one. As you could see, these are the regions where it is failing. It is only 90. Okay, let me make some changes into the model. Okay, able to see at this region it is failing completely. Right, so this is the most vulnerable region where the model is going to fail. Yep, so we need to remember that Gilbert is for ductile materials, we highly recommend, and Goodman is for brittle materials. Yeah, so I hope you already got this one. So how to deal with this and how to use the FESAFE solver to deal with the durability analysis. And once you solve the entire analysis, you need to just take that model into ABAQUS solver to just review the results. Okay, so hope you understood how to deal with the durability analysis by using the ABAQUS as well as the FESAFE solver. Yep, that's all about the session. Thank you all. Stay tuned. Bye, everyone.